Okay, section 15.8, Introduction to Complex Numbers. As you recall, going through this class, we have been introduced to, well, we've got real numbers, okay, which are all numbers. We have integers, okay, basically counting numbers. We have rationals, which we just learned about, and radicals, and irrational numbers. Now, we're going to get into complex numbers. So let's just take this very slowly, and it's not super hard, but it's probably the first abstract thing you're actually going to learn about in math. So let's scroll down here. Okay, definition. We've said this whole time that you cannot have a negative root. Well, I'm not telling you that you can. You can't have one naturally. We are going to create them. As a matter of fact, in the next chapter, I think even the next lesson, we're going to start creating negative roots. But what is going to happen here is whenever you see a negative, as you do right here, you're just going to, that all means that this, whenever you see this, whatever number this is, it turns into this. Once you see the examples, it's going to be all the more clear. And then once you see this, it just becomes that, which should make sense just from the last chapter. Notice that this, okay, is an inverse. So of course, whatever is under the radical sign just is left. Okay, that should make sense. So whenever you see shortly, not today, but shortly, whenever you see I squared, you know that that just means negative 1. Okay, I want to also point out something, that this right here is not a variable. Okay, this is an imaginary number. Okay, that's what that means. Okay, we're never going to solve for I. We're never going to try to get I by itself. Okay, this is imaginary. Okay, not a complex. This is an imaginary number. Okay, we'll get to complex very, very shortly. Okay, if A is a positive real number, then negative A equals A times that. You know what? I'll just show you an example real quick because let's get rid of the math. If you have something, for example, that looks like this, negative 2. Well, I can write that. Notice that is not a perfect square. So I can write this as negative 2, or sorry, 2I. Just make sure, look right here, that the I is not under the radical sign. Okay, especially because of Hawks. Hawks will count it wrong. What would happen if we had a perfect square? Well, if I have a perfect square, like say I have negative 4, well, that's still a perfect square. So I can change that 2. I can do the square root of 4 and get 2, but I've still got this negative I got to deal with here. Okay. Well, remember, once you see the negative under an even root, okay, you just pull it out, and it becomes I. Okay. Let's continue on. Here is the definition of complex number. In fact, let me kind of shrink that up just a little bit so we can get all into one screen. Okay. The definition of a complex number is A plus BI, where A and B are real numbers, and where A and B are real numbers. A is called the real part, and B is called the imaginary part. We just learned what an imaginary number looks like. We know what real numbers are. Real numbers can be anything. Okay? If B equals 0, then A plus B equals A plus 0I equals A is a real number. Okay. Continue on. If A equals 0, then A plus BI equals 0 plus BI equals BI. It's called a pure imaginary number. or just an imaginary number. Okay. A lot of your homework is going to delve with this right here. Okay. This right here, that is a complex number. Okay. You'll see it look like this. Let's just do an example here. You may have a regular normal 2 plus the square root of 4i. They could look like that. Notice I have my real part, and then here I have the imaginary. Okay? Both of those put together create the complex number. Okay? Because I do show it in class, I want to go and show it now. Then we'll get to some examples, which will make things a little bit more clear. Let's give myself some room. This is not something you need to know for your test. We'll just kind of call this extra knowledge. Okay, you know what an XY plane looks like, and the reason why these are the way they are, these complex numbers, is because we actually use a different coordinate plane. I'll show you. Let's just create a plane here, and I've got Y, and I have X, and then I can have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. Okay, normal plane, you've got your X, and then you've got your Y. So let's kind of come over here. 1, 2, 3, 4. Let's graph something at 4, 2. Okay, so we go 4, then we go up 2. I've got a point right here. On the complex plane, this is your I plane. So you kind of say your y-axis is your I plane. So notice this would actually not just be y, okay? This would be 2i. This would just be I. This would be 3i. This would be 4i. This right here on your x-plane is literally just 1, 2, 3, 4, 5, 6, ... Okay, so to graph this, or to show this as a address, let's just put it that way, this would be written as always the x value first. 4, well, notice I have a positive 2i, so positive 2i. That's how we show that. Now, I can point to this. Okay, let me show you where you get the word conjugate from. Since it's a little bit easier to show, let's go in the exact opposite direction. Let's graph it here. Well, notice we still are at a 4. Okay, but now we are at negative 2i, so minus 2i. That is what it means to have a conjugate. Okay, graphically, that's exactly what that means. I want you to see this, though, because if you'll notice, your real part, let's see here, real part equals an x value. Your imaginary equals a y value. Maybe that'll help you understand the standard form and how things need to look. Because your standard form, everything needs to be in that shape, because that's the address of where this actually is on a graph, just not a graph that you're used to seeing. So we'll get through these. We'll get through some of the examples, and hopefully it'll kind of make a little bit more sense. Like I said, this is something we're going to jump into, learn it, and then kind of move on. It'll just be part of our vocabulary moving forward.